Welcome to Deeksha Online. This is JEE crash course and we are discussing numerical problems based on mechanical properties of solids and fluids in today's class. While doing synopsis, we have already covered the essential concepts and the related equations. Now it's the time to put them all into use. Let us see how to understand the applications. Let us take some numerical examples. First one, two equal and opposite forces F and minus F act on a rod of uniform cross-sectional area as shown. The shearing stress on the section AB will be, okay. So here is the construction. A force F here and another force F here, and the angle subtended at this point is theta. The angle subtended at this point is theta. This is section AB. This is of cross-sectional area A. Now, we are supposed to find out the shearing stress on the section AB. The shearing stress is equal to component of force parallel to AB divided by the area AB. Let us simplify it further. So observe that force is along this direction and this angle is theta, and therefore this angle is theta. So we have, what is this? This is nothing but F cos theta. This is F and this is nothing but F cos theta. So we have F cos theta here and the area under consideration. So what is the area under consideration? Let's look at it. So what is this? So this is A and this is theta. So you have A cos theta, rather A by cos theta. So this is going to be F divided by A into cos square theta. So F divided by A into, sorry, this is nothing but sin theta, A by sin theta, my fault. This is nothing but A sin theta, A by sin theta rather. That is, we have cos theta into sin theta. So F divided by A into cos theta into sin theta. Thus the shearing stress is nothing but F divided by A into sin theta into cos theta. So which option does it correspond to? F divided by A sin theta into cos theta corresponds to option A. Example 2. A steel wire of length 20 cm and cross-sectional area 1 mm square is clamped at both the ends. The coefficient of linear expansion for steel and Young's modulus are given. If the temperature of the wire is reduced from 40 degrees centigrade to 20 degrees centigrade, the tension developed in the wire is. So we are looking at the thermal tension. You know that thermal stress F by A is given by alpha y delta T, or say delta theta. So thermal stress, or rather the tension developed, thermal tension is equal to alpha y A delta T. Are we given the value of alpha? Yes, 1.1 into 10 to the power of minus 5. Y is 2 into 10 to the power of 11. Cross-sectional area 10 to the power of minus 6. And the temperature change is 20, and this simplifies to 4 into 1.1, that is 44 into 10 to the power of 10, that is 44 Newton. So 44 Newton is the thermal tension developed in the rod or the wire. So 44 Newton is the answer. Example 3. A light rod with uniform cross section of 10 to the power of minus 4 meter square is shown in the figure. The rod consists of three different materials whose lengths are 0.1 meter, 0.2 meter and 0.15 meter, and their Young's moduli are 2.5, 4 and 1 into 10 to the power of 10, of course, Newton per meter square respectively. Assuming that the string connecting the blocks and rod does not elongate, match the following. Now we have to find out, it's actually a combination of, we can say, 4 questions. That means displacement of point B, displacement of point C. So I'm just taking this option here. Displacement of point B, displacement of point C, displacement of point D, and displacement of the block. So it's all about finding the displacement here, right? So it's all about finding the displacement. So I'm just writing it here. So how to find out it? It's a very simple problem. In fact, to find out it, we consider the expression for Young's modulus, which is given by F divided by A divided by delta L divided by L. So what do I have? I have delta L is equal to F divided by A, and this is L and this is Y. So the elongation is FL divided by AY. FL divided by AY. So now it is all about finding the elongation of each rod. Elongation of each rod. Remember, this is a light rod, which means that the force acting on each rod is equal to mg. What is that? 10 kg into 10, 100 Newton. That is right. And suppose I consider elongation of AB, the rod AB, which actually gives me the displacement of the point B. How do I do that? 100 Newton. Length of that rod is 0.1 meter. Its cross-sectional area 10 to the power of minus 4. Its Young's modulus 2.5 into 10 to the power of 10. So I can find out the value of delta L of AB. Likewise, I can also find the increase in the length of the rod BC, increase in the length of the rod CD. I am actually taking you through the approach, and I want you to take up the calculations here. That's a work for you in fact. So now notice the question is about the displacement of the point B, C and T. So if I show the construction here, this is point B, this is point C and this is point D. And notice that displacement of B is equal to delta L of BC. That's correct? Yes. Displacement of C is equal to increase in the length of this is AB. I'm sorry, this is AB. I should write AB. Displacement of point C is increase in the length of AB plus increase in the length of BC. So B moves down because of the expansion here. C moves down because of the expansion of AB as well as BC. That's right. Displacement of the point D is delta L of AB plus delta L of BC plus delta L of CD. So we can find out the displacement of point B, C and D. And what about the displacement of the block? The displacement of the block is same as the displacement of the point D. Hope the idea is clear. It's actually a simple problem because the rod, all the rods are light, each one of them experiences the same tension. So if you simplify it, you will get this option. That means if I show it, go back, I will show it. This is what you get. A corresponds to R, B corresponds to Q, and obviously C and D should correspond to same thing. Do you agree or not? Because it's about displacement of point D and the displacement of the block. Both of them are same, so clearly C and D should correspond to the same quantity. Example 4. A stone of mass M is attached to one end of a small wire of length L and cross-sectional area A. So length is L here, and cross-sectional area A suspended vertically. The stone is now rotated in a horizontal plane such that the wire makes an angle theta with the vertical. The increase in length of the wire, if its Young's modulus is Y, is okay. Now, when this physical, rather conical pendulum starts rotating, this, when it is here, what are all the forces? You have got mg and tension, and this is theta. Thus, this being theta, we have t cos theta, and t sin theta is in this direction. So, we have t sin theta provides m omega square r, and t cos theta is balanced by mg. That's right. Now, so we have t is equal to mg divided by cos theta. You already know the value of mg and theta is given. So now the elongation is equal to fl divided by ay. That's right. The question is about the increase in the length of the wire, which means elongation, fl divided by ay. The force is nothing but the tension which is elongating it, so TL divided by ay. So if I simplify it further, T, the tension is nothing but mg by cos theta, y divided by a into y, or we have mg, it is L, mg L divided by ay into cos theta. This is the elongation of the wire, which is nothing but mgl divided by ay cos theta. mgl divided by ay cos theta. B should be our correct choice. Example 5. If in the above question the Young's modulus of the material is y, then the value of extension x is okay. So in this problem, corresponding to this, it is suspended like this. So we have 2t sin theta is equal to w. And for small angle, you know, we can write 2t into sin theta is equal to WL, right? For small angle, you know, sin theta can be approximated as tan theta, and that is also approximately equal to theta. But from the triangle, we can write tan theta is equal to approximately equal to theta, which is approximately equal to x by L. So I have 2t, x divided by L is equal to W, or t is equal to WL divided by 2x. But you know, stress is given by force per unit area. So we have WL divided by 2AX. Now, Young's modulus is stress by strain. What is that stress? Stress is WL divided by 2XA, and the strain is nothing but 2L square divided by x square. So Young's modulus is nothing but WL cube divided by AX cube, or x is equal to W divided by AY to the power of 1 by 3 into L. So this is the value of Young's modulus. Option D is our correct choice. Example 6. A cube of side 20 cm is floating on a liquid with 5 cm of the cube outside the liquid. If the density of the liquid is 0.8 gram per cc, then the mass of the cube is okay. So here is the construction. This is a cube of side 20 centimeter is floating with 5 centimeter of the cube outside. So this is 5 centimeter. The rest are all 20 centimeter. This is 20 centimeter. This is also 20 centimeter. So the liquid is occupying up to this level. Okay. Now, according to the laws of flotation, weight is equal to upthrust. What is the weight? The weight is nothing but volume into density of the solid into G. This is weight of the liquid displaced, which is volume of the liquid displaced, into density of the liquid into G. Right? So we can simplify it further. This is V, which is 20 centimeter cube into density of solid. Density of the solid is to be found out. We can directly find it out because we don't need this one. So this entire thing becomes M. M is equal to volume of the liquid displaced. What's the volume of the liquid displaced? Volume of the liquid displaced is volume of the solid inside. What is the volume of the solid inside? Volume of the solid inside is 20 centimeter into 20 centimeter into 15 centimeter. Correct? How? The volume of the solid inside is corresponding to a cuboid of sides 20 centimeter and 15 centimeter. 5 centimeter is outside. Into density of the liquid. So I'm just writing it here, 0.8 gram per cc. So take care of the conversions into G, that is 10. And of course this G and this G cancel. So we're left with M is equal to 20 into 10 to the power of minus 2 into 20 into 10 to the power of minus 2 into 15 into 10 to the power of minus 2 into 0.8 gram 10 to the power of minus 3 divided by per centimeter cube, that is 10 to the power of minus 6. If you simplify it, we get it as 4.8 kg. So the mass of the object or the cube is 4.8 kg. Example 7. An airtight container having a lid with negligible mass and an area of 8 cm square is partially evacuated. If a 48 Newton force is required to pull the lid of the container and the atmospheric pressure is 1 into 10 to the power of 5 pascals, then the pressure in the container before it is opened is. Simple problem. It says there is a lid and this lid is light, and it says that area is 8 cm square. 48 Newton force is required to pull the lid off. Atmospheric pressure being 1 into 10 to the power of 5, I'll call this pressure as P. You know that force is nothing but pressure difference divided by area. Sorry, the other way around. Pressure is force divided by area, or this is the excess pressure or the difference in the pressure. So I can write force is equal to delta P into A. What is the delta P? P minus, that is P inside minus P outside into A. What is that? This is 48 is equal to P inside is P minus 1 into 10 to the power of 5. And what is that? So if you look at this equation, this is how much? That area is given as 8 centimeter square. Right? 8 centimeter square. So minus 4. Right? So this is nothing but the equation which helps me in getting the value of P. So P is equal to, in terms of atmosphere, 0.4 atmosphere. Okay. Example 8. If the air density were uniform, then the height of the atmosphere above the sea level to produce a normal atmospheric pressure of 1 into 10 to the power of 5 Pascal is very simple. He says pressure of 1 into 10 to the power of 5 Pascal should be produced, and the hydrostatic pressure is given by rho g h. So h is equal to P divided by rho g, that is nothing but 1 into 10 to the power of 5, density is 1.3 and this is 10, and you can simplify this and it turns out to be 7.7 into 10 to the power of 3 meters, or h is equal to 7.7 kilometers. Fairly simple calculation. 7.7 kilometer is the height of the air column required to produce normal atmospheric pressure. Example 9. In a horizontal pipeline of uniform cross section, pressure falls by 5 Pascal between 2 points separated by 1 kilometer. The change in the kinetic energy per kg of the oil flowing at these points is... Okay, let's see how to do this one. So now if you look at it, the Bernoulli's theorem tells us that P1 plus half rho V1 square is equal to P2 plus half rho V2 square. The question is about finding the change in kinetic energy per unit mass. So we can write P1 minus P2 divided by rho is equal to half V2 square minus V1 square. So if I look at this delta, change in kinetic energy per unit mass. So remember, this is, I have to divide it by mass. So we have P1 minus P2 divided by rho divided by m, right? So, or I can multiply it by this one. So this is nothing but change in kinetic energy divided by mass per unit mass. So this entire term, if you look at it, I can multiply it like this: half m V2 square minus V1 square divided by m. This is nothing but change in kinetic energy per unit mass. So change in kinetic energy per unit mass is nothing but P1 minus P2 divided by rho divided by m multiplied by m. So we simply have P1 minus P2 divided by rho. And we have all the details here, right? 2 points separated by a distance of 1 kilometer. So that means the change in pressure is 5 pascals and the density is also known to us. So you can simplify this, and this change in kinetic energy per unit mass is, if you simplify the earlier equation, you get 6.5 into 10 to the power of minus 3 joule per kg, of course. Remember that distance has no effect here. That distance of 1 kilometer has no effect because this is a horizontal pipe. That's redundant data. Question number 10. The velocity of the wind over the surface of the wing of an aeroplane is 80 meters per second, and under the wing it is 60 meters per second. If the area of the wing is 4 meters square, then the dynamic lift experienced by the wing is, okay. again, the dynamic lift is given by F by A, which is d by 2 into V2 square minus V1 square. What is this? This is nothing but the expression. So we can simply write it as d by 2 into V2 square minus V1 square. So the dynamic lift experience, that means force, is d by 2 into V2 square minus V1 square into A. Now do we know all the details? Yes, this is 1.3 divided by 2 V2 square 80 square minus 60 square into area of the wing is 4 meters square. So I can simplify it further and it turns out to be 7280 Newton. So the dynamic lift which tries to lift it up is 7280 Newtons. B is our correct choice. Example 11. Calculate the velocity of efflux of kerosene oil from an orifice of a tank in which pressure is 4 atmosphere. The density of kerosene oil is 720 kg per meter cube and 1 atmospheric pressure is 1.01 into 10 to the power of 1.013 into 10 to the power of 5 pascals. Simple question. Velocity of efflux is given by square root of 2gh, right? And this is, see, how to find out that value, velocity of efflux from an orifice of a tank in which pressure is 4 atmosphere. Now suppose this is atmospheric pressure and this point is at a pressure of 4 atmospheric pressure. Yes, right? So that means the liquid pressure is rho gh is equal to 3 atmospheric pressure. So I can write it as 2gh. H is 3 atmospheric pressure divided by rho g. From this expression we have H is equal to 3 atmospheric pressure divided by rho g. So now we can simplify it further. You know the value of the density. This becomes 2. G and G cancel. 3 atmospheric pressure 1.01 into 10 to the power of 5 whole divided by density. What is the density? The density of the oil, kerosene oil, is 720 kg per meter cube. So upon simplification you get this value as 33.55 meter per second. So speed of efflux from this liquid, or say from kerosene at that point, is 33.55 meter per second. Example 12. A metal plate 100 cm square in area rests on a layer of castor oil 2 mm thick whose coefficient of viscosity is 15.5 poise. The horizontal force required to move the plate with a uniform speed of 3 cm per second is. This is a plate and there is a oil layer which is 2 mm thick, and you want to move this one. That means the top layer of the castor oil moves with the same speed v, and the bottom layer is in contact with the surface on which it is present. The force exerted by the viscous or say viscosity is given by eta A dV divided by dy. So how much? Eta 15.5 poise into area 100 centimeter square into the velocity gradient. What is that velocity gradient? 3 centimeter per second. That means the top is moving at a velocity v, the bottom is at 0 velocity. Therefore, the velocity difference is 3 into 10 to the power of minus 2. Over what length? 2 millimeter. So, the viscous force which is given by eta A dV by dy is given by this numerical value, and it simplifies to 23,250 dyne. So, if I retain everything in CGS, look at these options. Options are all in terms of CGS units. So, I don't have to convert anything into SI. I can just retain it in the CGS system, and upon simplification, we end up with 23,250 dyne. Example 13. The total area of cross section of the blood vessels is 0.25 meters square. If blood is flowing at a rate of 100 centimeter cube per second, then the average velocity of flow of blood through the capillary in millimeter per second is. Okay. So notice that the volume of the liquid flown per unit time is given to us. That is total volume of the blood flown per unit time, which is generally represented by Q. And that is nothing but AV, you all know that. So now average speed is dV divided by dt whole divided by A. But what is this dV by dt? That is the volume rate flow. 100 centimeter cube per second divided by the cross sectional area is 0.25 meters square. So you can simplify this, and this turns out to be 0.4 into 10 to the power of minus 3 meter per second, or 0.4 millimeter per second. So the average speed turns out to be 0.4 millimeter per second. Example 14. The velocity of a ball of mass m, density d1, when dropped in a container filled with glycerin of density d2 becomes constant after some time. The viscous force acting on the ball is. Okay. In case, if I consider the forces, what are all the forces? The forces are mg and of course upthrust, right? And he says that this is drop. So what is the direction of viscous force? This is the direction of the viscous force. And can I write viscous force is equal to mg minus upthrust? Yes. And do you know how to simplify this? mg minus, or mg into 1 minus d2 divided by d1. This is nothing but the density of the liquid, and this is the density of the solid. You may wish to recall that this is given by mg into 1 minus sigma divided by rho, and hence mg into 1 minus d2 by d1 is the viscous force acting on the object. Mg into 1 minus d2 divided by d1. Simple problem. 15. An air bubble of radius 1 centimeter rises with a constant speed of 3.5 millimeter per second through a liquid of density 1.75 into 10 to the power of 3. So we'll read as 10 to the power of 3 kg per meter cube. The coefficient of viscosity of the liquid is, okay. So he says that it rises with a constant speed. That means it is moving at terminal speed. You know that terminal speed is given by 2 by 9 into r square into sigma minus rho. It rises, so sigma minus rho into g divided by eta, right? This is terminal velocity. Therefore, eta is equal to 2 by 9 r square into sigma minus rho into g divided by terminal velocity. Now, do we know all the details? 2 by 9 into r square, 1 centimeter into the density of liquid is 1.75 into 10 to the power of 3, right? Liquid of density this much, coefficient of viscosity of the liquid is, so I can say this is 0 divided by Vt. What is that equal to? That Vt is nothing but 3.5 into 10 to the power of minus 3. By the way, why is this 0? That is air bubble, and it says that the density of the air is negligibly small. So if I substitute these details, what do we get? 10 to 109 Newton second per meter square. That is the coefficient of viscosity. So coefficient of viscosity is 109 Newton second per meter square. Okay. Next question. A body of mass 10 kg is attached to a wire 0.3 meter long. Its breaking stress is 4.8 into 10 to the power of 7 Newton per meter square. The area of cross section of the wire is 10 to the power of minus 6 meter square. The maximum angular velocity with which it can be rotated in a horizontal circle without breaking is. Okay. So we have to whirl it in a horizontal circle without breaking it. And it says maximum breaking stress is given. So if I consider this, the tension provides the necessary centripetal force. That's right. So necessary centripetal force is given like this. So now, suppose I consider this one. This T divided by A is equal to m omega square r divided by A. This is nothing but breaking stress. So I write it as m 10 kg omega square, which we have to find out, into r. What is the value of r? It is 0.3 meter divided by A, that is 10 to the power of minus 6. And this breaking strength is equal to, according to the problem, 4.8 into 10 to the power of 7. So I can equate these two and find the value of omega square, and that omega square gives us the value of omega eventually, which is 4 radian per second. So the maximum angular velocity with which the system can be rotated without breaking is 4 radian per second. 17. Two wires of different materials, each of length L and cross-sectional area A, are joined in series to form a composite wire. If their Young's moduli are y and 2y, then the total elongation produced by applying a force F to stretch the composite wire is. Okay. So now the total elongation is elongation of first plus elongation of the second. That's right. What is that equal to? In general, delta L is given by FL divided by AY. So I'm going to write it as F L1 by AY1 plus F L2 divided by AY2. F by A can be pulled outside along with L, 1 by Y plus 1 by 2Y. So it further simplifies to FL divided by A, 1 by Y plus 1 by 2Y gives me, what is that? 3 by 2Y. So 3FL divided by 2AY. So the total elongation of this entire system of two composite rods is 3FL divided by 2AY. 3FL divided by 2AY. Next one. As shown in the figure, in adjacent figure, of course, if a load of mass m is attached to lower end of a wire, lower end of the lower wire, find the displacement of the points B, C, D. Right? Now let us assume that each rod is light. So we have seen a problem of this kind. How to do this? Suppose I consider this wire. This segment is A, B, C and of course D, and a weight is suspended here. If the elongation of this is delta L1, delta L2 and delta L3, then the question is about the elongation of different wires, right? So now how to find it out? We have already done that. Delta L1 is equal to FL divided by AY. So is the force same all along? Yes. What about their cross sectional area? Same. So I'll write this is L1 by AY. And here the question is E1. Then find the displacement of the points. So displacement of the point B is delta L1. Displacement of the point C is delta L1 plus delta L2. Displacement of the point D is delta L1 plus delta L2 plus delta L3, where delta L2 is the expansion or rather elongation of this and this respectively. So we notice that it's a pretty simple problem, and in fact here all of them are correct. So all the options are correct. I want you to work out it in detail. Okay, simple problem that is. Example 19. One end of a long metallic wire of length L and cross-sectional area A and Young's modulus Y is tied to the ceiling. The other end is tied to a massless spring of force constant K. A mass M hangs freely from the free end of the spring. It's slightly pulled down and released. Its time period is given by OK. So the arrangement is like this. You got a wire. Its length is L. Cross-sectional area is A. Young's modulus is Y. Other end is tied to a massless spring of spring constant K, and a mass M hangs free. And this is pulled down and released. We have to find out the time period. Simple once again. Now if we are able to find the force constant of this wire, this being known, I'll write as K1, K2 is equal to K. So if I get this, I have the answer directly. So now it is as good as two springs connected in series. And you know, if two springs are connected in series, then effective spring constant is given by K1 K2 by K1 plus K2. So I need to find the spring constant of the first one. How to do that? It's simple. Now if you look at it, this is Young's modulus is given by FL divided by AY. That is delta L, of course. Delta L elongation is given by FL divided by AY. Or F divided by delta L is equal to, what is it going to be? YA divided by L. But F divided by delta L gives us force constant, that is spring constant. So K2 here is equal to YA divided by L and K1 is equal to K. Therefore, K equivalent is equal to, what do we have? K1 K2 by K1 plus K2, that further reduces to K YA divided by KL plus YA. I have found the value of K equivalent. And now the time period is 2 pi root M divided by K equivalent. 2 pi root M into KL plus YA divided by KYA. So the time period of this arrangement is given by this particular equation. And what is that? 2 pi root M into KL plus YA whole divided by KYA. Option D is correct. 20. The volume of oil contained in a certain hydraulic press is 0.2 meter cube. The compressibility of oil is 20 into 10 to the power of minus 6 per atmosphere. The decrease in volume of the oil when subjected to a pressure of 200 atmosphere is, okay. So here change in volume is equal to change in pressure and V divided by bulk modulus. That is delta P into V into compressibility, which is represented by C. So the decrease in volume. So you notice that the volume is given, compressibility is given, and the extra pressure is given 200 atmosphere. I am just substituting it straight. I want you to take care of the conversions. Volume is given as 0.2 meter cube and the compressibility is 20 into 10 to the power of minus 6 per atmosphere. So you can simplify it further and you can show that it turns out to be 8 into 10 to the power of minus 4 meter cube. That is the decrease in the volume of the liquid. So decrease in the volume of the liquid is 8 into 10 to the power of minus 4 meter cube. So everything is meter cube, of course. So B should be our correct choice. 21. When a polar bear jumps on an iceberg, its weight, 200 kg weight, is just sufficient to sink the iceberg. The weight of the iceberg is given that the specific gravity of ice is 0.9 and specific gravity of seawater is 1.02. Again, from loss of flotation, weight is equal to upthrust, that is weight is mg is equal to volume into density into g, right? So the weight is equal to, so how much is that? So you can simplify this. Then the weight of the iceberg, is, you can simplify it further here and everything is known here, so you can substitute and get the value of weight of iceberg. I'll leave the calculations to you. I want you to complete the calculations. By the way, the answer turns out to be 1500 kg weight. You can try it for yourself. That's your practice problem. 22. An iceberg is floating partly immersed in seawater of density 1.03 gram per centimeter cube. If the density of ice is 0.92 gram per centimeter cube, then the fraction of total volume of the iceberg above the level of seawater is. Again, same thing. This is seawater and iceberg is present like this. Suppose delta V is the volume outside and V is the total volume. He is actually asking you what is delta V by V. That is his question. Fraction of the total volume above the level of seawater. Now, according to the laws of flotation, weight of iceberg is equal to weight of seawater. Weight of iceberg is equal to weight of seawater. What is weight of iceberg? That is mg. Weight of seawater, volume of the liquid displaced, that is delta V, into density of seawater into g. Mass is nothing but mass of the iceberg is volume into density of iceberg into g. So delta V, density of liquid into g, these two cancel, and therefore we have delta V by V is equal to density of ice divided by density of liquid. So you know both of them. Density of ice is how much? That is 0.92 and this is 1.03, and of course if you convert it into percentage, what are you going to get? You get it as nearly 11%. So 11% is above the level of seawater. Example 23. A large cube of ice 4 meter thick has a vertical hole drilled through it and is floating in the middle of water in a lake. The minimum length of the rope required to scoop up a bucket full of water through the hole is. Okay. A large cube of ice has a vertical hole drilled through it. So I'm just considering the cross-sectional view. This is a cross-sectional view. Now a hole is drilled through it. So what happens is that the level of water is available up to this. So he is actually asking you what is this length. He is asking you what is this length. That means he is indirectly asking you what is the value of, or what is the side of this ice cube above the surface of water. So if you understand the question, it becomes pretty easy. Again, weight of the iceberg is equal to weight of the liquid displaced. What is the weight of the ice? That is, if I take the side as L cube into density of ice into G is equal to weight of the liquid displaced corresponds to this part. So this is x into L square into density of water into G. So these two cancel, and therefore x is equal to L into density of ice divided by density of water. One set of L square goes. So we're left with L. What is that L? The cube, ice cube is of side 4 meter. Density of ice is 0.9. And how much is that? Divided by 1. So you can simplify it further. Right? So this is 3.6. So 3.6. Right? So x is equal to L. One set of L is gone. So density of ice divided by density of water. Density of ice is 0.9. Density of water is 1. So this is 3.6 meters. Right? Or 360 centimeters. This should be D. Example 24. A rectangular block of wood of density 800 kg per meter cube having a mass of 2 kg is pushed into water so that it is completely submerged and released. Neglecting the viscous forces, the initial acceleration of the block is okay. So there is a rectangular block and its density is given, its mass is given. Now what are all the forces? Its weight and upthrust. Acceleration is equal to upthrust minus mg divided by its mass. What is upthrust? It is volume of the liquid displaced into density of the liquid displaced into g minus m into g divided by m. But volume of the liquid displaced is same as volume of the solid. Volume of the solid can be written as mass of the solid divided by density of the solid. So I have m divided by density of solid into density of liquid into g minus mg divided by m, or it is simply rho L divided by rho s minus 1 into g. So you can substitute here. Density of the liquid is known to us, and of course m is also given to us, even though it's not required completely. So upon simplification you get initial acceleration is equal to 2.5 meter per second square. Example 24. A rectangular block of wood of density 800 kg per meter cube having a mass of 2 kg is pushed into water so that it is completely submerged and released. That is the answer that we got is 2.5 upward, of course. 25. An aeroplane of mass 5000 kg is flying at an altitude of 3 km. If the area of the wings is 50 meters square and the pressure at the lower surface of the wings is mg into d1 plus d2 divided by d2, the pressure on the upper surface of the wings in Pascal is okay. I think we will this data seems to be incorrect, so we need the value of this pressure, the area of the wings, and the pressure at the lower surface of this is required. So I think there is something wrong with the data as far as this question is concerned. We'll skip that one. Okay, so with that problem we have come to the end of this session. So remember, this is one of the very important chapters from your JEE examination perspective. Please practice all these problems one more time and then try to understand that this chapter is mostly an equation-centric chapter. So you need to memorize the equations along with the concepts as well. All the best. Thank you very much.